Hey Trig class, let's get back to it. In 8.4 we're going to look at the trig form of complex numbers. So what is a complex number? A complex number is just a number that consists of two parts. It has a real part and an imaginary part. So the reality is all our real numbers are complex numbers. They just have a 0 right here for this b. So a and b are real numbers. And then the imaginary part has this I, which is the square root of -1, if you recall. That's what the imaginary digit is. So if I had the number, say, 5 minus 2i. So what that means is the real part is positive 5. Right, so that's a, that's 5, so that's over here in between the 4 and the 6. And the imaginary part is b, -2. Alright, so that would be that point right there. And that's how we would plot it. 5 minus 2i, when we plot it in what we call the complex plane. And these units along the what look like the y-axis, the up and down axis, they have i's. This is imaginary, this is real. So that's that number. Now, when we plot a number, a complex number, we describe its magnitude. You know, what's the magnitude of a complex number? And it's just like with real numbers. It's its distance from 0. So the distance this thing is from 0 is its magnitude. Okay, and we typically use z, the letter z, to represent complex numbers. So like x is the typical number we use for like an unknown real number. Z is a very common thing to use for an unknown imaginary number. So this imaginary or complex number is 5 minus 2i. And then, just like the notation we used before, what's the magnitude of z? What's the magnitude of this complex number? It is how far this complex number is from the complex number 0, 0. And notice we get the Pythagorean theorem here, right? We get a right triangle. And the sides of that right triangle, this is -2, or in absolute value 2. And this is 5, and we'll be able to use the Pythagorean theorem to come up with the magnitude of this number. Alright, so the magnitude, just like we said, we square the a part, we square the b part, and then we take the square root. So -2 squared plus 5 squared, and that last one we did would be 4 plus 25. Alright, the square root of 4 plus 25 would be the square root of 29. And that would be the magnitude of that number. Alright, it's its absolute value. It's how far that number is from the origin of the complex plane. So there's the one that we just did. Oops, actually I had that reversed. I meant to do that number and I had my signs reversed. But we just saw that one was, this is a, this was b, so that was the square root of -2 squared plus 5 squared, which was 25. So we ended up with the square root of 29. Alright, and then this one over here, same thing. This is a, this is b. So we square each part, add them together. So we get the square root of 10. So there are the ways to find the magnitude of the complex numbers. Alright, and then finally these set notations. This is all the numbers in the complex plane. Z, whose absolute value is less than or equal to 1. Alright, and then this one is the same thing. All the values, all the complex numbers whose magnitude is less than 1, but b, the imaginary part, is greater than 0. So let's do this, and then this is just a subset of this. They're just a different subset. But if we do part A, well, this is the imaginary, this is the real. So imaginary is up and down, this is the real. But the magnitude being 1 just means it's 1 unit away. So if we go out 1 unit on the real axis to the number 1 that we're used to, the real number 1, and we just made that a radius of a circle, that would be every point whose distance is less than or equal to 1. It's just like the definition of unit circle. How do I get this? The magnitude of z is the square root of a squared plus b squared. Well, square both sides and you would get so the square root of a squared plus b squared, that's z, is less than or equal to 1. If you square both sides, you get a squared plus b squared is less than or equal to 1 still. We're just squaring both sides. Just getting rid of that square on the other. But 1 squared is 1. And that looks like a circle with radius 1. And that's what we get right there. Okay, so for part B, what's it asking me to do for part B? It's asking me to do the things that only have the imaginary part greater than 0. So it'll be the top half of this circle. Alright, so it's the top half of that because we only want the things that have a real, the real part of the imaginary, the complex part, to be positive. Alright, so here's the big thing that we're going to talk about here. The trig form of these. And these last couple of slides hopefully got you thinking that, especially this idea that, if I'm out here, I can for all these things, these complex numbers who have a magnitude of 1, I could be right there. And like I said, I could drop a perpendicular. There's the magnitude. There's the straight line distance from the origin. That's the absolute value. But I can drop a perpendicular down and I create a right triangle. And then, like we said in the polar section, if I have a point, I can come up with a polar version of that point. Alright, so this is z. This is the complex number. This is the magnitude of z. This is, what we could call r. Right, and then this is cosine and sine, again, because right now we're in the unit circle, but we could come up with a polar form of this point just because we have a real part, an imaginary part, and we're in a plane, so it's just like the polar coordinates of a point is how we're going to come up with the polar version of these complex numbers. So a lot of this should look somewhat familiar. So the magnitude of z, we said that's kind of like r, and the notation that we've been used to, like polar forms of numbers. So r cosine theta, well, that's like x, plus I magnitude of z, that's like r sine theta, that's like y. So the polar form of the number is just like the x coordinate and the y coordinate with this plus sign between them, and I to indicate that's the vertical axis now. So it's very similar to what we just did. Alright, the magnitude of z, like we just said, that's like r, so that's the square root of a squared plus b squared. Alright, we saw in the last section r squared equals a plus b if our point was ab. Same exact thing. And tangent theta, b over a, the y part over the x part, the imaginary part over the real part. Alright, and that angle is called the argument. That's something that you'll hear me say a few times in here. So theta, we refer to it as the argument. But it literally is, you're going to see with these examples that it looks a lot like just polar forms of numbers. Alright, how do we come up with the trigonometric forms of these complex numbers? Well, for a, I need to find r and theta. So the magnitude of that is the real part. Negative 1 squared is 1. This is 1i, so b is 1. 1 squared is also 1. 1 plus 1 is the square root of 2 underneath the radical square root of 2. And then this is negative, so we're moving to the left. Like if I drew the unit circle, we're moving to the left 1, so that's negative 1, and then up 1 for positive 1i. So we are in what we used to call quadrant 2. It's still quadrant 2 in the complex plane. And we need to know what makes, remember the tangent of, the tangent is equal to, right here, negative 1 1 divided by -1, b over a. So tangent's equal to -1 in quadrant 2, so that's 3 pi over 4. Alright, so how do we write it? R, or magnitude of z, cosine of theta. Theta is 3 pi over 4 because we're in quadrant 2. I sine 3 pi over 4. And that's all we have to do for that. It's again, what would if this was not imaginary numbers, if this was just the point -1, +1, in the last section, if this was just -1, 1, what would be the polar form of this number? It would be, r would be square root of 2, right, and then theta would be 3 pi over 4. So that's what we did in the last section. And all we're doing now is we are putting this number out in front, and we're putting this number in for theta in the middle there. If you can remember that, just don't forget the plus. We do a plus bi. You're going to be golden here, because that's the link between the two, is taking it from its polar coordinate, if this were the point -1, +1, to the fact that it's an imaginary or a complex number. You just go to this notation, put the cosine and the sine back in there. Alright, and then for part B, same thing. So we have a 3, 4, 5 triangle, and we talked about that the angle with a 3, 4, 5 is not a perfect angle. It's not one of those angles like 30, 60, 90, 45 that we see on the unit circle. So it's this weird angle, and also it's negative. Okay, this is quadrant 4, so it's giving us a negative angle, but we want the positive version of that. Okay, so I would add 360 to this to get back into quadrant 4 and get the positive version of that angle. So remember, that's coterminal. We're just adding 360. So there's r, and there's the cosine theta, I sine theta. And again, it's just the positive version of that angle to get us something that's not got any negatives, kind of neats it up a bit. Alright, write the complex number. So this is in polar form, in standard form. So what do? Well, the nice thing about this is literally just order of operations. So multiply this out. This is r cosine theta. This is r sine theta. There's your x part and your y part. You just need to find the cosine of pi over 6, the sine of pi over 6, which is respectively square root of 3 over 2, 1/2, and then multiply by this 2. So what's going to happen, we're going to end up with this thing, and then when we multiply by the 2's, we're going to get rid of those denominators, and we'll get the square root of 3 plus I. And that's all you have to do with that one. It's just literally evaluate. Think of it like an order of operations problem, and this is like the variable that makes it to where these aren't like terms and you can't combine them. So you're just simplifying as much as you can there.